All right, we need to, let's start here and let's look at another, it's a logarithm and an exponential. A good place. Let's see. All right, so let's say we got the function y equals 5 to the 4x times log base 5 of 8x. All right, and so as we see a lot, we've got a product rule here. We're going to find the derivative. Okay, so the derivative of 5 to the 4x, that's an exponential, a to the x, we're looking at there. Well, the good thing is the derivative of a 5 to the 4x starts with 5 to 4x. Itself is part of its derivative. All right, but since it's not base e, we got base 5, what else do we need? ln of 5. So we need ln of 5. Also, because unless it's base e, your exponential is base e, you're going to have this ln of the base. And then what else for the derivative of this? Derivative of the power, right? So derivative of the power, derivative of 4x is 4. So all that is the derivative of 5 to the 4x. And so since it's product rule, we have to leave that second one as is, and then do a second round here. Start with the 5 to the 4x and do the derivative of the log base 5 of 8x. Okay, so what do we got there? Well, log base 5, we know, I'll just write it up here. So the derivative with respect to x of log base a of just x, well, ln of x, the derivative is 1 over x. Any other log base a, log base 2, log base 3, it's 1 over x. Also, you also have 1 over x, but since it's a different logarithm than the natural logarithm base e, we also need in the denominator there the log base natural log of a. Yeah, the ddx of ln of x, should start with that one, I guess, but is 1 over x. But at any other base, you got 1 over x, but then you have that extra little piece. That's all that, I guess, really it amounts to. So that's what we've got here, right? We've got a separate, a different base logarithm, base 5. So you need, now this is, instead of x, we've got 8x, so it's 1 over that 8x. You see what I'm saying? And then that's times then the natural log of the base, which is in this case natural log of 5. But again, it's a chain rule, so that's the derivative of the outside, so you got to do the derivative of the inside. What's the derivative of 8x? Just 8. And really, the second part's the only part that cleans up, right? Because I can do a little canceling there. I believe that's all. So, yeah, they probably write the 4 first, since I'm going to rewrite it. 5 times 5 to the 4x times natural log of 5 times log base 5 of 8x. Plus, how are you going to write this? 5 to the 4x over x ln of 5. Maybe some more we could do to clean that up. I was thinking about that. Actually, if I use the change of base theorem, that would clean up a little more. Yeah. See what I'm saying? Because it'd be ln of 8x over ln of 5. So, yeah, you know.
Is that acceptable, though?
That would be acceptable, yeah.
Right.
That'd be acceptable, but you can always look for other things, probably. Okay, now, one other thing about logarithms is, you know, ln of x, log base a of x, we mentioned this before, but the x is limited. If I have ln of x, what I'm saying is the x is limited. X has to be greater than 0, doesn't it? And so when you're doing your derivative here, like over here, okay, so it's not really stated, but I guess it might be should state it. We should state it, because really, when I'm saying 1 over x there, you know, it's an x that comes from this function, and so the x has to be greater than 0 there. So this wouldn't work for negative values of x. But that just kind of sort of goes without saying, but just to mention it. Now, there is one thing to point out, though, that it really has more to do with the antiderivative than the derivative, but we'll kind of go at it. We'll look at the derivative and then make application to the antiderivative, okay? And that is this, okay? So if I put an absolute value there, so do the ln of absolute value of x, what is that? What is that going to be? Well, if we go back and think about some things here that we talked about way back, if you took Calc 1 with me here, we wrote the absolute value of x as piecewise. So let's do that here. All right, so let's say, well, okay, so this function, I want it to be, all right, so absolute value of x, so it's ln of x if what? Well, just x, if x is greater than 0. It's the ln of negative x, okay, so that's the negative, if x is less than or equal to 0, let's call it, doesn't matter where you put the equal to, but, well, actually,
Say it can't equal 0.
yeah, it can't equal 0, so just forget that. So it's just 0, less than 0. Remember, we just substituted the x, x is greater than 0 minus x if it's less than 0. That's how we did it on the piecewise. Okay, so as far as the derivative goes then, so the derivative of the ln of absolute value of x, well, let's just do the derivative of these. If it's x greater than 0, what's the derivative here? It's ln of x. What's the derivative?
1 over x.
It's 1 over x. If it's less than 0, then I'm taking the derivative of ln of negative x. What would the derivative of that be? Well, it would be 1 over negative x times what else, though? This is a chain rule, isn't it?
Negative 1.
Times negative 1. The derivative of the inside. Okay? What is that, though?
1 over x.
That's 1 over x. Hey, how about that? It doesn't really matter which piece you're on. The derivative is 1 over x. Whether it's x greater than 0 or x less than 0. So doing the ln of the absolute value of x. So this kind of opened up, because now what x's can this be? It can be anything except 0. This can only be greater than 0, but you see this can be anything except 0. Well, it turns out, though, even in that case, the derivative is still 1 over x. Whatever x is. Okay, so, like I said, that you probably won't have any where you have to do the derivative of an absolute value of a natural log. The natural log of absolute value of x. However, if we look at it going the other way, the antiderivative, that's what this really is here to show you, okay? Because here's what this means. All right, so let's say I've got the integral 1 over x dx. I'm wanting to do that integral. Hopefully you see then that besides x equals 0, the integral, which is the antiderivative, would be what? So this is saying I want a function here whose derivative is this. That I want the antiderivative. What function has its derivative as 1 over x? ln of absolute value of x. You see, that's a better function than this is. I mean, it's kind of the same thing here, except, right, that's 1 over x, except x has to be greater than 0, you see. So we could say it's just ln of x, but isn't ln of absolute value of x better? Because that gets more x values involved. You see what I'm saying? So the function whose derivative is 1 over x, in other words, the antiderivative of 1 over x is, we're going to say, ln of absolute value of x. And then since it's an indefinite one, it's plus c. Okay? Now this, not only that, this fills in our kind of our missing piece for the powers of x, because another form of this antiderivative here, I guess you could say, or integral, it's the x to the negative 1 power. And remember on our power rule, if you have x to any power, it's 1 over n plus 1 times x to the n plus 1 plus c, except negative 1, right? This is the missing piece. So now we know if x is the negative, n is not negative 1. So this fills in that piece. Now we know what happens when n is negative 1. It turns into this natural log business, natural log of absolute value of x. Okay? Works for any, and it works for positive, negative x's. Just not 0 because the function isn't defined as 0. All right? Okay, well, this of course opens up other integrals based upon use substitution, really. You might say. All right, so let's look at a few other integrals here. Okay, so we've got 4x over x squared plus 6, and it's dx, integrating with respect to x. Okay. We haven't talked a lot about functions where you have division, but we have mentioned, I've mentioned a lot, that you can't just do the antiderivative of the top over the antiderivative of the bottom. We know that's out. Okay, that doesn't work. So, yeah, we have to come up with something else. So, and we'll look at some more with the fractions here, but this one actually is one for use substitution. You kind of always want to try use substitution if it's not a, kind of an automatic, hey, that's a power rule, or you know what I'm saying. You always kind of want to look for, first of all, use substitution. Well, I guess we haven't done a whole lot. So what would you think the substitution would be?
Denominator.
Denominator, yeah. Yeah, in ones like these, use substitution when you said do what's in parentheses. Well, I guess we could write it where it's in parentheses, but that's not actually here. Yeah, in ones that look like this, try u as the denominator. Yeah, u equals x squared plus 6. All right, so then du would be what? 2x dx. And so divide by 2x. I usually kind of shorten it there. So my dx is du over 2x. That's what I'm going to replace by dx by. Okay, so the 4x kind of comes along, then the u is the denominator, and dx is du over 2x. Hey, this is going to work, isn't it? For this to work, we need this x, whatever I have down in here, it needs to cancel out with something over here. As long as that happens, it works. And sure enough, that x cancels with that x. Leaves me a 2 here. So I wind up with, don't I have 2 over u du? Hey, that's a whole lot simpler. And matter of fact, it's something, yeah, the reason we're mentioning it here is because what is that antiderivative going to be? Yeah, instead of 1, we got a 2, but that doesn't matter. It can be any number here, as long as you got number over x. And you pull out the 2, it's 1 over u. So, yeah, you're with me there? So it'd be 2 times, that 1 over u, so the antiderivative is ln of u, right? ln of absolute value of u. And then indefinite, so we add the plus c there. Okay, with me there? All right, now, go back and resubstitute what u is. Wasn't u x squared plus 6, so make that. So that's a pretty good answer. What we might note here, though, on this particular case, it's not in general the case where we can do this, but in this particular case, do you see, we're talking about real numbers here. X is real numbers. X is a real number. So if I plug in a real number here and then add 6, what am I going to get? A positive number, aren't I? There's no way, if it was minus 6, I could get sometimes get negatives, but x squared plus 6, that's always going to be positive. Are the absolute values then necessary? No, because that's not going to change. As long as this is going to be a positive, so sometimes you can, sometimes you'll say, well, why don't they have the parentheses? Well, the absolute values, they have parentheses. Well, in this case, we don't need the absolute values because, is it wrong to put those there? No. But it's simpler since we don't need them, to write it that way. That's probably how to do it. Okay. Okay, yeah, so let me show you this one. Maybe you're familiar with, maybe not, but there are some properties of logarithms that sometimes they'll utilize. So let me just mention those. Here for you. We could have used actually one on that one, but that is when you can kind of condense, or sometimes you need to expand. You can condense and expand logarithms a number of ways. If you have the log base a of x plus log base a of y, say. Okay, so it's same base logarithm, and the two logarithms are added. Well, it turns out the sum of two logs can be condensed to a single logarithm by multiplying the x, in this case the x and the y. So those two can come together, a log plus a log, same base, can come together by multiplying the inside parts. If you have subtraction, log base a of x minus log base a of y, they come together as division. And then the third one is if you have a number out front, this is the one that we could have used in one previous example here. In that case, if you have a number out front of a logarithm, that can come in and be a power of the x. And so sometimes doing that makes sense going, the way I described it was going this way, but you can also go the other way. You can take this and expand it to that, so if you're not that familiar with those, be aware, because we will use those from time to time. And that's what I was saying, we could have used, and that's what made me think of it, we could have used one of those here. Which one could we used here? 1, 2, or 3?
3.
We could have used 3, yeah. We could have used 3 here on this one because we could have said, well, let's go ahead and bring that in and make it an x squared plus 6 squared. And is that any simpler? Yeah, probably not, but sometimes those types of things do. All right, so let's try another integral here. Integral 1 to 3 of 5 over 3x minus 5 dx. So again, it's division, quotient. You can't just do antiderivative, divide by antiderivative, unfortunately. That'd be really nice, but it doesn't work. So again, we're going to do the u is the denominator. U substitution where u is the denominator. So that would make du, what's the derivative of 3x minus 5, which is just 3 times dx. And so divide by 3, and that gets me my dx. All right, and this one's a definite, so you just have to remember the limits here are not u's, they're x's. So you can change them to u's. I don't care if you do that, but if you don't, those are x values. So, all right. So what have we got? What have we got in this case? Well, nothing cancels, but essentially what I've got 5/3 times 1 over u, don't I? Then you can write it that way. If we can pull out the 5/3, that's, sometimes you'll see them do that. You know what I'm saying? So the 5 and 3 don't cancel, but that's not going to stop us here from using natural log, is it? So it's 5/3 times the ln of the absolute value of u. And then we're going to go from x equals 1 to x equals 3. And so yeah, that's where be sure, those are x values, not u values. We're not ready to plug in those yet because we don't substitute those for u. It'd be 5/3 times the ln of the absolute value of 3x minus 5. Then we can go 1 to 3, can't we? And the absolute values here are necessary, aren't they? Because, yeah, that could be a negative value. And so the absolute value allows us to do, even though we have a negative value for 3x minus 5, the absolute value will allow us to do an ln of that. And I think one of these numbers does give me a negative. The 3 was that ln of absolute value of 4, and then the 1 would be the ln of absolute value of -2. So yeah, that's what allows me to do the 1 here. It's because it's absolute value. So it's just 5/3 ln of 4, absolute value of 4 is just 4, minus 5/3 ln of just 2, which is a pretty good answer. I mean, we can evaluate that, approximate that, whatever we need to do. However, there is a simpler answer here where we don't even have to approximate because, well, maybe I have to factor off the 5/3. Then you can see it. What can I do here?
Division.
Yeah, property 2, right? That's 5/3 of the ln of 4 divided by 2, or just 5/3 ln of 2. How about that? So, you can say, well, I got this answer, the book got that answer. What's it say? Okay, it's going to be the same same value. You know, one way you can see if it's the same is evaluate that out and see if you get the same decimal as that. See if you do have the right answer, or just remember the properties and do it anyway. So, all right. Okay. One other nice, we had the 1 over x that filled in for us the integral of 1 over x dx. Well, another one, having done this, that kind of gets filled in, I guess you might say. And I believe it's on the formula sheet that I provided you there, that you can use on the test. It's the integral of tangent x dx. We can actually figure that out. It's not a nice antiderivative, integral of cosine of x dx and integral of sine of x dx. Those are nice antiderivatives. This one it's not that nice. It's not too bad though. But the reason it comes up here is because the way you figure this out is you know that tangent of x is sine of x over cosine of x. That's one of the identities we have. But if you do u substitution on that, again, u is the denominator. Look at what du is. Negative sine of x dx. And so, what you find up with is sine of x over u times du over negative sine of x. This is going to work with that u substitution. It's just negative 1 over u du, right? That's a natural log, isn't it? I guess we'll go ahead and finish. It's not that. So it's minus, so the antiderivative would be minus ln of u minus ln of absolute value, which u is cosine. That's not how the answer appears though. By properties of logarithm, if I bring in the minus 1 power here, what is this right here?
Secant.
That's secant. So it's ln of the absolute value of natural log of secant of x. That's the one that appears on the formula sheet there. It's because of u substitution and the natural log. Okay. All right. So we want to take a look at another technique here. Let's take a look at what's known as logarithmic differentiation. Logarithmic differentiation. A good place to utilize logarithmic differentiation is one example is this, where we have kind of a dilemma here because we've got x in the base and x in the power. So are you going to say that's an exponential, or are you going to say that's just a power? Are you going to use the power rule, or are you going to use the exponential rule? I'm talking about the derivative here, doing the derivative. Well, the answer is you can't do either because it's both, I guess, at the same time, sort of thing. It's a transcendental function, sometimes these are called. This is a good candidate for the so-called logarithmic differentiation because, you can't use the power rule and you can't use the exponential rule because it's got both of them at the same time. Okay, so this is one reason for doing the logarithmic differentiation. The principle basically is this. You're going to take the ln of both sides. Logarithmic differentiation, pretty much what you're going to do is you're going to start by taking the ln of both sides. So I'm going to ln this side, ln this side, ln both sides. And maybe you can see the reason for doing that is because what can I do now to the right side? It's kind of going the other way from what we were doing before, but I can alter this a little bit. I can bring that power out. It's going to get rid of that power, if you will, because I can't bring it down here, but since it's in a logarithm now, I can bring that power by that property 3 that we just mentioned. It's usually the third property of logarithms that see that? Now I don't have the same problem, so now I can talk about the derivative. However, on this side, you know, I have it, instead of just y, I now have ln of y, so I have to deal with that. But it's now basically on this side, well, both sides, I guess, but it's a implicit d dx both sides, the d dx both sides. So what would the derivative with respect to x be there? It's an ln of y. What would the derivative be? ln is 1 over y. But since it's a y, I'm doing the derivative with respect to x, I need dy over dx. Yeah. Okay with that? What about side number 2 here? The right side. You've got to use product rule. That's x to the 1/2, so it'd be 1/2 x to the minus a half for its derivative, but I have to do the ln of x derivative separately, right? And then over here, so the second would be the square root of x times the derivative of ln of x. Well, that's just ln of x, so it's just 1 over x. Now, the goal was, I guess I didn't write down what we were doing here. We're trying to find y prime, the derivative. So, solve for dy over dx, multiply both sides by y. So we have dy over dx equals y, you can do whatever you want to with that. We can flip that over, make it square root of x in the denominator, right? Can't do one. Now this, you can do a little subtraction of the powers. You got x to the 1/2 in the top, x to the first in the bottom, so that's x to the minus a half also right there. With me there? So that's a pretty good answer. Usually though, when we want to get the derivative of y, we have the answer in x if we can, and we can because y is just x square root of x, x to the square root of x. So that's usually how you see the answer. And then write those however you want to. But okay with this? Logarithmic differentiation. Yeah. I flipped some things over. I don't know if it's better or not. Okay, another one where this is good for is one where you kind of have, well, I'll just show you. So find the derivative. Since we're kind of going between integrals and derivatives a lot. Find the derivative. It's y equals x squared times x minus 3 to the 4th over x plus 5 to the 6th power. Logarithmic differentiation is actually a good one for that too. Here's why. Okay, so logarithmic differentiation, what do? Take the ln on both sides. So I ln y, and that equals the ln of x squared times x minus 3 to the 4th over x plus 5 to the 6th. Okay. All right. So, what does that do? Well, on this side, by the properties of logarithms, this side over here, it doesn't, I don't know if you call it simplifying, but it's going to simplify the derivative quite a bit because it's going to make, if I didn't, okay, so I didn't mention it, but if I just did, all right, let's just do the derivative of that. What do you got? Quotient rule, product rule, you got a big mess is what you got. It's going to be yay long. You divide by x plus 5 to the 6th. That would simplify x plus 5 to the 6th squared, so it'll be x plus 5 to the 12th. The answer here is much, much simpler than x plus 5 to the 12th in the denominator. It would cancel quite a bit out. So that's what I'm saying. This is going to make it a whole lot easier to get to a simpler answer. I guess what I say. All right. So what do we got? So we've got ln of y. So this side now, what we can do with that with the properties of logarithms, you see here by properties of logarithms what I can do. I've got a product, so I can split those up into this. This is kind of the expanding mode of properties. So since I've got the top is the natural log of that product, you see. And then we've also got the dividing, so we've got the ln of a quotient, so it's the ln minus the ln of that. Yeah, the derivatives of these